So let's go ahead and do Anova. All right, so I will be up front. Anova can be kind of difficult to wrap your head around, but I will say is that, and this is one thing I think the curriculum doesn't really explain well by itself, is Anova really are just like t-tests. And really Anova is just another generalized linear model, but also abbreviated GLM. But basically just know that Anova really is just using multiple t-tests. In reality, too, is that Anova is really what is an F-test. So for example, I think the curriculum mostly uses stats models to do Anova, right? You can do Anova in sklearn, but note that there will be no, if you search for Anova sklearn, you'll find that there's no function formula for it like in sklearn. And that's because it's really using F-tests. So that's kind of like the basis of like what I'm kind of talking about. So this is going to be a little bit different from like what the curriculum shows. But I think a good way to kind of talk about Anova is that basically it's just saying, let's see how I say this. You're testing to see if there's a difference between different groups. Okay, so I think Wikipedia has a great article on showing this. And so I'm going to show this picture. So this is kind of representative, like you imagine this yellow group on the left here is basically all the population. I think in the Wikipedia it talks about like different dog breeds and stuff like that, and maybe like their weight or something like that. So you imagine like the y-axis here is like the weight of dog breeds, and X1, X2, X3, X4 are representative of the different breeds. So you imagine like a Labrador, I don't know, a Basenji and whatnot, right? So this on the left is all that collection together, basically the distribution of this part. And it's not super obvious that like maybe it's normal, maybe it's not. And so you decide to split it up in different groups. And so what you want to say is like, hey, is there actually a statistical difference between the different dog breeds, between dog breed A, B, C, and D, right? And what you can do then is you have these different parts, and you can kind of look at this right here, is you can probably see there's not a huge difference between these parts, but like it's not super obvious, right? So what we're gonna do is basically quantify what this looks like. So the way this kind of goes through is when we're doing our Anova tests, what we're going to do instead is actually say, all right, what's the difference between, or what's the variation within its group? And then what's the variation of the groups from the overall mean, right? So what this looks like, let's see if I get a good color. Let's do red. Red probably do fine. Okay, so if you imagine here, like we have a certain variance in here. So you imagine here's the mean right here for the overall population, all of it together. And then you can see the different means, for example, are different. In this case, it looks like Wikipedia made it really obvious. Like, okay, all the means are very, very straightforward right here. Okay, and then what we say, okay, what's the variance basically within these different groups? Like how far is it basically from with the group in here? And essentially you take all of the stuff like how this one varies with itself, how this one varies within the group, how this one varies within the group, and basically combine that with the overall look of this guy. And if there's a difference between that two, then you say there's an overall difference somewhere in the distribution. Note that Anova and F-test doesn't tell you directly what thing, like where's the biggest difference from it. It just says, is there a difference or not? Your alternative, like your null hypothesis essentially is like if I had like the mean of X1, the mean of X2, the mean of X3, and the mean of X4. Okay, we're basically our null hypothesis is saying that these are all equal to each other. So our alternative, does anyone guess what the alternative is?
At least one is different.
At least one is different. So basically the alternative is that these are not all equal to each other. Note that doesn't mean that they're all different from each other. It just means that at least, like Jeffrey said, at least one of them is different. One of these things is at least different from the rest of it. So note that kind of like that is what we're doing with an Anova test. Okay, so it's kind of important distinction between those two. So in this graph right here, you can probably see that there's really not gonna be any difference. But if we had something like this one right here, this one is a little more clear that, okay, there's gonna be some difference. So what we're gonna do essentially is we're going to measure across each point right here and say, okay, from this drawing right here, if we have this right here, it's like, okay, this is our average on this guy. This is our average right here. This is our average right here. This is our average right here. And this is our average right here. So essentially what we're going to do is measure two different things. I'll make it in two different colors to make it a little clearer. So I'll use red first. So basically red will represent, say, okay, how far away is each one of these points from the average. So let's say I have this average overall. How far away is each of these groups from this point right here? So you can imagine finding like the residuals from this average right here. So we have this one value. And then what we do, and I'll draw this in, let's try pink. No, let's try purple. Yeah, that seems good. Okay, so from purple, we're gonna basically measure, say, okay, within this group, how far are the data points? If you imagine they're different data points, what is the difference within this group right here? And this will give us a different value. So imagine like basically all the residual sum of squares in here, that's gonna give us some value. So I'll call it like Q, just a Q1. And this right here, all the different values in here, how does the average from here depend on each different point? So we'll have like Q2, and then Q3, and Q4. No, I'm just using Q just because I don't want to use a variable that we'll use, like a value that's commonly. So Q is not typical. But essentially what we do, we sum all these parts together. Oops, wow, that's an awful sigma. There we go. Okay, so we're summing up Q1, Q2, Q3, put those all together and say, okay, this is how basically all the different groups vary amongst themselves. And then we compare it with this ratio saying, how do the groups vary amongst all of them together? So essentially we take that and use that ratio called an F ratio, and that will give us essentially our F statistic, a new letter, a new test. So an F statistic, and we use that to say, all right, is this statistically significant from it? And that's what the Anova is really doing, is saying, is that significantly different? Note that this one right here might give like, say, oh, it's gonna be maybe like, let's say a p-value of like 0.04 compared to an alpha of 0.05. So like, like, oh, it's significant, right? But maybe not super significant versus something like this next graph right here, is going to be a lot more significant. You can see there's a lot more, there's smaller amounts of variance within these different individual groups. So that's kind of like how these would be compared through. Okay. Does that make sense? Like conceptually what's going on? Cool. Any questions on at least the conceptual idea of like how this Anova is working? Okay, cool. All right.
Sorry about that. But Anova, it's comparing the variance of each. Okay.
You can imagine like it's comparing how does these different groups vary amongst themselves and compared with the overall group. So basically, is this group different from the overall population? That's really what we're trying to do with Anova.
Can you, so you were looking at mean in the example, but can you look at other statistical the statistics tied to those populations, like the variance in the actual population itself, or standard deviation, or is it just the mean?
I think you're saying because I use like mu right up here, right? Yeah, so usually what we're saying is like, is this population different from, are these samples, these different groups, different from the overall population? And in that case, we usually use like something like mean. I guess you could technically use something like a median. And I guess you could if you really wanted to say, is the standard deviation different from each other? But the main thing we're trying to figure out is there's always going to be some difference. Like it's never going to be exactly, the population mean is never going to be exactly the same for every individual group. And you want to see, is that statistically significantly different? So I would say generally, no, you wouldn't use it on other metrics. Like, is the variance different from itself? Because they always will be different, right? Because the variance is going to include, for like, this overall population is going to include all possibilities versus like a subset, which likely, like technically they'd be the same if they were like a similar, like little tiny population. But we already know from random sampling that's likely not to be true. That will probably have a variance that's going to be actually smaller. So it wouldn't make as much sense to compare them in that way. But good question. Okay. But Anova does take into account that these different groups will have different variances. So that's the nice thing about it, is that since these will all have different variances, it will actually look at saying, it will consider that these will have different variances and will have essentially a different spread, different groups. Cool. All right, so I try to like, I try to keep, when I do this Anova talk about it, I try not to like talk too much about the math because I think it's not relevant to what we're going to do. But know that if you look it up, you'll see this part. But basically, like I mentioned, the F statistic or F ratio is used to get the p-value. So just like we had a z-test, right? T-test, we have an F-test, right? So you can basically see they're all very similar. Essentially, we're going to use this distribution called the F-test, the F distribution, to get an F statistic to determine our p-value. which will say, is it significantly different? So like I said, we're basically just going to say, how much do those individual groups vary amongst themselves? How much do the groups vary? I'm sorry, how much do the groups vary from the overall population? And then we actually do a measurement of how much the groups vary within itself. So you can imagine this, what's it called, the residuals, right? The sum of squares between the groups. So if you had like 5 groups, you'll have 5 different sum of squares, like 5 different residuals, add them up together, but you could have like many, many groups. You could have 100 groups, right? And then you would say, how does the residual sum of squares happen within the group itself? So just know, like, I'm just gonna avoid the math, so we're not gonna do that. And basically our F statistic basically will say, hey, how does it compare with each other? So how much do the residuals of the groups themselves vary from the overall group? And that will give us our F statistic. And again, I'm not gonna kind of focus on that mathematical part, but basically that's our F statistic, and that will tell us our p-value, okay? Some quick thing assumptions, as always, like to go through. For the record, usually we'll tend to kind of forget, like in practice, we'll tend to say, oh yes, assumptions are true, even when they're really not. Just kind of be aware of that. But we assume that the samples are independent from each other, right? Each sample is from a normally distributed population. So note that we're assuming that our population overall, but that usually is not a huge concern, since we can always think of the central limit theorem, that we can basically always take a sample of our samples, and essentially that will give us a normal distribution. So for the most part, we kind of tend to ignore this part. The biggest thing is that our population standard deviation of the groups are all equal. Basically knowing that our residuals are homoscedastic, right? So there's no heteroscedasticity in our residuals within our different groups. So this is very similar to like when we talked about like probably like linear regression and stuff like this, or other parts of like, you know, essentially any other statistical test that we do. Okay, make sense so far? Like, I kind of put this more as a side note versus like really talking about this. Note that if you don't have these assumptions, you can technically do these other tests. There's like, for the record, there's like so many different statistical tests you can do. But there's like, you know, this is what PhDs in statistics can like go in forever. For the most part, you're probably pretty safe in using most of the tests that we talk about, at least in practice. Okay. So how do you say about seeing an example then? Not a good deal? Cool. So I realize I only have about 5 minutes. So, okay, before I kind of continue forward, let's hear what's tomorrow's section is sections 23, right? Which is on, can someone remind me what section 23 was on? Okay.
Bayesian statistics.
Okay, Bayesian takes a while. All right, so, all right, we'll see what we can do right now, and then maybe we'll continue some of this stuff for next time, because that'll be kind of a good kind of practice going forward. But I kind of want to show you guys a little bit how doing SciPy, since that's usually a little more common in my opinion than stats models, which is what the curriculum shows. But I'll kind of show you a little bit. This is based off of the F1 way. So remember, Anova doesn't actually exist in, what's it called, in SciPy. So we're going to just use the formula from here. So I'm just going to go show you this part. So just kind of know that I'm basing off this. These values, don't worry where these kind of came from. This came actually from this example here. But basically, these are the different normalized values for, in this case, these are different, I think, muscle shells. So like the different sizes of the muscle shells going forward. And we're just saying, are there different, are these different values? So these are kind of like from different areas. Do the muscle shells differ from each other, at least in size? So I'm just creating this data set. So this is not normally what you do. You'd already have the data fed in from a CSV. But I'm just kind of putting this because it's already from an example. And then just basically a data frame. And you can see up our data frame here is basically a different area. And then the shell, which is a standardized value, just to make it a little bit easier and more typical. So the important part now is like, okay, let's see what these, how they look. So these are probably a little bit different from what you have seen before, maybe. But we've seen a box plot. I'm using Seaborn here. But you can see here I'm doing a box plot of the area. So the area is going to be our different box plots, so our different groups. And then our Y is going to be our shell standardized, since we only have one feature here. And I'm just changing some extra features like the color and the line width. And then this right here is swarm plot. So I think this is important to kind of show you guys. So, oh, I should have known that. That's okay. So let's go ahead and plot this guy. You can kind of see right here, this is our box plot, and you can see a different distribution. Tillamook, Newport, Petersburg area, right? So these are different areas. But it's kind of nice to show a little bit of like the distribution. So one thing we can do is a swarm plot, which actually plot out the individual points. So you can see here, in this case, I put this in yellow, you can actually see a little bit of the distribution of where these points are. Note that like within here, you see how they're kind of like staggered. That means absolutely nothing. It's just make it easier for us to view those data points. But you can see here a little bit of the distribution versus like if I just went like these combined together, hopefully give more information. I mean, just a swarm plot. Like this kind of gives in a value, but like I think between the swarm plot and the distribution box plot together, it makes it a little bit easier for us to see that distribution. Another way we can do this too, that's kind of similar, is a violin plot. Have you guys seen violin plots already? Okay, cool. So you can see a similar violin plot, and I made a little bit, little extra like emphasis, so it's a little bit easier for us to see those distributions. And I always like to put the little distribution on top of it so you can see where those data points actually come from. Okay, so we can probably see from here, like, you know, some of these values, like this one probably are very similar to each other. This one too, but this one, yeah, I don't know, this might be a little bit different. So we can actually run an FWA1 test, right? And we just basically pass in all the data for the SciPy. We run this guy, and this will tell us basically our p-value. And our p-value in this case is 0.0002, which means significant, which means there is a statistical significant difference between these different groups. Okay. So that's kind of like essentially how you would run your F1 way. So you can see your Anova test can be very quickly. Now, once you know that there is a significant difference, this doesn't tell you which one is statistically significant. In that case, you would actually run multiple t-tests to basically go through. And you wouldn't just go multiple t-tests first because you might accidentally, come across the fact that like you, what's the word for it? You might accidentally get some false positives when you really shouldn't have it. So that's where an F1 way test is a little more robust to basically say, hey, is it worth me investigating further and to say, are they different from each other? Okay. Cool. Does that make sense, everyone? All these, like just kind of showing this little plot and then actually doing that F1 way.
So in this one, as we're doing the F1 way, it's comparing the variances against each other to see if there is a significant p-value across those 5.
Yeah, the p-value is just basically saying, is there a significant difference between these groups from the overall group together?
Yeah. And so for the F test, we don't need to worry about calculating power or setting the alpha value or anything like that.
Right. Well, how do I say this? You can, for example, quote the, like, how do I say this? You can technically talk about the power and stuff like this, but it's not necessarily the main focus of like, you know, trying to figure out through analysis of variance if this is actually significant or not. In the same way that for most hypothesis tests, you probably don't necessarily need to quote the power level. Sometimes people do, but it's not necessary for the most part, if that makes sense. I'm trying to think of a better answer to that, but I would say in practice, probably not. You wouldn't use like state the power and stuff like that, just because you don't necessarily need to. It's not the main focus. Okay. Yeah. So the way I kind of see it, Anova is kind of like getting you to the point of like, okay, is there a significant difference? And then say, is there a significant difference? Yes, there is a difference. Okay, let me go ahead and investigate further with multiple t-tests. In this case, you can maybe actually do either all the t-tests, or you can probably look at the ones that you have most interest. For example, maybe Petersburg area is what we really care about. So I'm going to see a t-test between the Petersburg area and Newport area and see if there is a statistically significant difference between these two different groups. So you can think of it like analysis of variance as saying, is there a significant group of, like, are one of these groups significantly different from the overall population? Okay, cool. All right, so I do have to head out to another meeting and everything like that. Feel free to keep asking me questions on Slack and everything like that. I think the next part I would do is like we would go through a little bit of like how to create this from scratch for Anova. So maybe we'll do that next time. Otherwise, we'll go into Bayesian statistics, which usually takes a little bit of time. There's quite a lot to go through. So we'll play it by ear, I guess, next time. Sound good? Cool. All right, everyone. Oh, I guess I'll go ahead and start recording too. So let me go ahead and stop that.